All right, today I'm going to show you how to use your data that you're getting during our Six Flags field trip. So this is really meant for an in-class activity where you have an actual accelerometer in front of you, but since you don't have it, you can just imagine. So this is how your accelerometer that you'll actually take with you on Mr. Freeze in the vest works, although it's a very rudimentary version. But if you just think about a weight here in a plastic tube and springs on either side that kind of hold it into place at position 0. And we're going to look at what that measures. So for some clues, if you were to turn the tube vertical, so that you're looking at the head to toe axis, which is something we're going to be talking about instead of X, Y, and Z. We're going to talk about head to toe, left to right, and front to back, because as you go on the roller coaster, you're going to be moving up and down and twisting all around. And so the axes are always going to be with respect to your head and toe, left and right, front and back. So this is what the accelerometer looks like when you just hold it vertically. This top spring has to be stretched more than the bottom spring in order to support the weight of that weight. So let's talk about what a reading of 1 means. Let's draw a force diagram for a person standing motionless holding this accelerometer. And I want you to tell me how big the normal force is on the person compared to the force of gravity on the person by the earth. You should have drawn a force diagram with balanced forces, force of gravity on the person by the earth acting down, force normal on the person by the surface acting up. So the net force on the person is 0. So we get a reading of 1 when the net force on the person is 0. So let's look at what this tells us. Now we're going to try something else. If you were standing still and you held the tube sideways in front of you level, so that it was like oriented front to back and the person is standing still, the tube's going to look like this, and the weight's not going to move. It's going to stay right there. So on your force diagram, how big is the force pushing forward or backward on the person compared to the force of gravity on the person? You should have found that that force is 0. So because there's no force left or right. So if we look back here, our force on the person in the front to back direction is equal to 0 times the force of gravity. And oops, I went the wrong way, sorry. And when we go back to this example, our force normal on the person is equal to 1 times the force of gravity on the person. Okay, let's go back. Okay, so the device is actually a force factor meter. The reading on the device will tell you the size of the push or pull force compared to the size of the force of gravity on you. The key to using it correctly is understanding which force it's measuring. So after obtaining your force factor readings, you can find acceleration using your force diagram. Let's do an example. So here is a person in a roller coaster car, and the Mr. Freeze car is going to accelerate to the right. Predict the motion of the force factor meter. So which way is this weight going to move? There he goes. And the weight moved to the left. You should know this because the weight has inertia, so it wants to stay at rest. There needs to be an unbalanced force on this weight to accelerate it, so the spring on the right is going to have to be more stretched than the spring on the left. So our net force has to be to the right in order for the acceleration to be to the right. Now let's draw a force diagram for the the rider. He's not driving. And we should see normal force acting up, gravitational force acting down, and a push force acting to the right, causing the person to accelerate. Let's find the acceleration. So first I want you to find the rider's weight. Next, I want you to find the forward push on the person using the force factor meter reading of 2.2. Next, I would like you to find the size of the net force acting on the person. And last, the person's acceleration. Here are those answers and solutions. Quick little question. If the guy sitting next to you, next to this rider, has a mass of 90 kilograms, what will his force factor meter read? You should have said that the force factor meter will read the same. It doesn't matter who is wearing or holding the accelerometer. The force factor is the same, and then when you plug in the actual weight of the person, that's where the net force changes. If we look back at this equation, we find our force of gravity, which has mass in it, and then later, when we solve for acceleration, well, that force of gravity is used to find the force factor, and then later when we use acceleration, we divide by mass again. So our acceleration should be independent of mass. They should both accelerate at the same rate, and the force factor is also independent of mass. Here's another example. Let's say that this car goes over this rounded hill. Which way should the meter go? And it goes up to the 0. The reason for this is we have to have a net force downward in order for the car and the person to accelerate in a circle with the center down here at the bottom. So let's draw a force diagram on the rider. And you should have drawn just a force of gravity down. We can tell that there's no normal force because the force factor meter, factor meter is at 0. So our net force on the rider should just, what should the net force on the rider be? And what should the acceleration of the rider be? Here's an example to think about. If the rider is upside down and going around this loop, predict where the force factor meter will go. And it has to go up. The net force has to be down towards the center of the circle so that the rider can make the curve. Go ahead and draw a force diagram for the rider. Just a quick reference frame check. Remember that the force factor meter and the accelerometer are going to be turning with the person. You're going to be wearing a vest, and that vest is going to be attached to your body. So that's why we're calling it head to toe instead of like up and down, because the meter is turning with you. So when the meter goes up, it's really going towards the person's lap. So the person would see it going down. Here's the force diagram for the person. Can you calculate the net force and the acceleration of the rider? All right, that's it. You will be getting some graphs from Mr. Freeze, and those graphs are going to have the force factor versus time instead of acceleration versus time. So you're going to have to use the force factor and the person's mass and draw the net force equation on them in order to find their acceleration at different points.